Piano.
Piano. All right, I don't have a piano here, but we're going to talk about string instruments, and the principle is going to be the same, even though technically a piano is a percussion instrument, right? Because it gets hit. Yeah.
I started out on soprano clarinet, switched to bass clarinet.
Yeah.
Also played my church chimes, which were 10-bell set. And one year I marched in the band playing a glockenspiel.
All right, so we'll have clarinets. I have a picture in the end for percussion. I don't know if we'll do bells. Anybody else? Yeah.
Guitar.
Guitar, perfect. Others? Yeah.
A flute.
Flute. We'll do some flute.
Violin.
Violin. We got other string instruments. Anybody? Yeah. Trumpet. I got a trumpet up here. Anybody else? Other instruments? Drums. Guitars. Yeah, drums. Guitars. Singing. Your throat and your mouth is a musical instrument. Guitar.
Singing.
And guitar. Yeah.
Yes.
Okay. We don't have any bassoonists here, huh? Or oboists. It's a stretch, but you can hope. Let's see, what other kind of obscure instruments can I think of? That's probably good enough. What else? Oh, French horn. Well, that's me. Yeah.
Harp.
Harp. Again, like a string instrument, like a piano, in that we're not going to change the length of the string, but the principle will be
Piccolo.
piccolo. All right.
Saxophone.
Saxophone. All right. So we got lots of interest right here in the room about musical instruments, and you got a sort of an intuitive sense of how it works. But what we want to look at is what's the physics, what's actually happening inside or on that instrument to make it happen. So what I need to do is start with waves. Let's do this, okay? And we're going to use my slinky here. Can I have a volunteer to help with the slinky? All right, come on over. Stand right. Yeah, stand right about there. And you're just going to hold that slinky, okay? And I'm going to go back here, and we're going to set different kind of waves going on this slinky. And I'm going to be careful of Sean's cello, okay? You might want to move it if I get too close to it, okay? Okay, all right, we'll be done soon. Okay, so we have longitudinal waves. That's a kind of wave where the motion of the wave, the motion of the material, is in the same direction the wave's going. So here's a longitudinal wave, okay? So in other words, I gave a compression to the end of this slinky, and you see a wave go down that way. What's your name?
Sarah.
Sarah, would you come up here instead of over there? Maybe it'd be easier for everybody to see if we do this sideways. I just changed my mind midway through. Okay, let's stretch out again. Okay, here comes another longitudinal wave. Ready? Okay, so it's a compression. You're listening to a longitudinal wave right now. Sound waves are longitudinal waves. The air is getting compressed, and because the air has a resistance to being compressed, it compresses the next set, it pushes back out, compresses the next piece of air, which compresses the next and the next and the next, and a wave goes outward from me to your eardrums, which bounce back and forth, and you sense that as sound. Okay? So you're listening to a longitudinal wave, a sound wave. We have a different kind of wave, and it's the kind of wave that goes on a string instrument, and for waves down in the earth, it's also a different kind of wave that happens down in the earth, and that's a transverse wave, where the motion of the material is perpendicular to the direction that the wave's going to go. So I'm going to send a transverse wave down here too, and I already forgot. What's Sarah? Okay, see, I didn't forget. Okay, so I'm sending a transverse wave, and actually there's a little twist-em on here, and you can keep an eye on the little twist-em, and what you can see is it's not the entire slinky that's moving up and down, that a particular particle on this will just travel. Oh, that wasn't a very good wave. Let's try again. Okay, here we go. Up and down. Okay, so if you see how that little twist-em's going, it just simply goes up and down. Its motion is this way, while the wave is going that way. Okay, so that's the kind of wave that a string instrument is going to do. Now, what I'm going to do next is to send a whole series of waves down here, and what's going to happen is it's going to bounce off of Sarah. Okay, that wave is going to bounce off of her and come back to me, and I would just want you to see what happens with this slinky here when we do that. Okay, so I'll just start sending waves down there. You can see them kind of going as they go along. And we've gotten to a point here where, now you're just holding completely still, right? Where we have, it no longer looks like it's traveling back and forth, right? What we have is what's called a standing wave. A standing wave is the summation or the interference of waves that are going in other directions. I'm going to come a little closer so I can control this a little better, okay? And it has to do with the frequency, how often up and down I'm shaking this slinky to get the signal started. I won't not even look. I'm just going to do this for a bit and see what happens. Oh, yeah, I already got it going. Okay, now if I just speed up things a little bit, you see it sort of gets messy, and you see the waves going back and forth, and I can eventually, whoop, there it is, get to a point where there's a very specific frequency back and forth where we now have a different standing wave. This one's different than the other one, right? So let's go back to the other one. Now I'll let you know the secret, how we do this, okay? The way I can do this, the way I know how to do this is I'm going to send a wave down to her, it's going to bounce and it comes back to me. At the time it comes back to me, I send another one down. Right? And then I can get this standing wave going. So the frequency that I'm going up and down here is the time it takes that wave to go down and back. All right? So now we have what we would call the fundamental mode, standing wave mode of this standing wave. Okay? If I go a little bit higher frequency, whoop, there we go, I get to what would be the next higher mode. I call this the first mode. The fundamental would be the 0 mode. This would be the first mode. And you can know that because here in the middle is something called a node, a place where it doesn't seem to be moving at all. And in between the nodes are antinodes. Is that on there? Yeah, well, yeah, antinodes, right? Okay, so that's just terminology. But that's how you can know which mode it is. Okay, if I just change the frequency a little more, I should be able to find the one that has 2 nodes. Hold really still, Sarah, okay? Is that it? It's really hard for us to see. Have we got, is that 2?
Yes. 3.
All right, so this would be the second higher mode, or it's really the third harmonic, but we call it the second higher mode. A little higher frequency, it gets harder to do. Okay, are we there? Well, it keeps messing up, doesn't it? This is because I'm getting tired. We got it? How many? Can you tell how many? I can't tell from here. All right. All right. Right. Okay, so you get the idea? Thank you. That was wonderful. All right. So we can get these standing waves set up, the summation or the interference of waves that are traveling back and forth, and at very specific frequencies, the amount of time shaking the thing back and forth, it will set up various standing wave modes. All right, so let's talk about string instruments for a moment. Oftentimes I use a guitar because lots of people at least noodle around on the guitar. But we have a cello, which is special. So Sean, you want to come up with your cello? Let's just hold it up so they can see. I think everybody probably understands how a string instrument of some kind works, but let's have a look. So what we have is a string, and it's fixed here, right? It's against the bridge here, and it's connected, it's placed there, and it's free in between. So there's the length of the string, all right? Now, when Sean bows the string, what it's going to do is start getting waves going back and forth, up and down that string. And those waves are going to travel back and forth at some speed up and down the string. It depends on how tight the string is and what the string is made out of. But when he does that, it starts setting up those standing wave modes. The mode is, if you can see this picture on the top, the wavelength of that mode, which would be like if you were to draw a sine wave, up, down, like that. So the wavelength is the length of this wave before it repeats, and that's twice the length of the string on the cello. So the wavelength of this string that he plays is about that long, right? So the fundamental mode, that thing that looked like a jump rope, right, has a wavelength like that. Half a wavelength is here because that's the one that goes like that. Okay? The next higher mode will have a node in the middle of it, like that. And the next one will have 2 nodes, and the next one will have 3, and the next one will have 4, and 5, and 6, and 7, and as many nodes as you like. Okay? And we'll see about all those harmonics. Okay. Did I say everything on here? I think so. So basically, the wavelength is twice the length of the cello divided by 1 or 2 or 3 or 4 or 5 or 6 or 7 or up to infinity. Right? What I want to do now, okay, here's the thing about the speed. The frequency. So frequency is important. That was how fast I was shaking the thing back and forth. When you hear music, the pitch that you hear is the frequency. Okay? The higher the frequency is, the higher the pitch. So your weight on there is really low. Okay? So frequency is related to pitch. The frequency is related to the wavelength. It's 1 over the wavelength. So the longer the wavelength is, the lower the frequency, and therefore the lower the pitch. The higher or the shorter the wavelength, the higher the frequency and the higher the pitch. Okay, so we have different kind of frequencies depending on the speed of the wave going up and down the string. So for a given string, that number would be fixed. We've got 2 times the length of the string times this n, where n's 1, 2, 3, 4, 5, depending on which mode we're looking at. Okay? If you shorten the string by putting your fingers down on it, you're just changing the length of the string, changing this. So making L smaller will make the frequency higher, will make the pitch go up. Okay? So, okay, keep hanging on there, Sean. One more thing. So there was that fundamental mode. We had the next higher mode. Its frequency is twice as high. A doubling of frequency in music is an octave increase in the pitch. Okay, so a doubling is an octave. So we had the fundamental mode. An octave higher is the first higher mode. The next one with 3 is a musical fifth above that. The next one above that is an octave because it's a doubling of a doubling. The next one is a third above that. I can't reach anymore. So then we have this one, which is a doubling of the third. This one's kind of odd. It doesn't really fit too well. There's another octave because that's a double of a double of a double. Oops, there it is. And then they keep getting closer together. All right? So these are all for a particular length of string. These are all the possible modes and therefore pitches that we're going to be able to hear on that string. All right, so the question you're asking yourself is, if Sean plays his cello, which one of these frequencies, which one of these modes are we going to hear? So let's find out. All right, what I'm going to do is switch off here to pull up a nice free program called Audacity. I've got my microphone here. You might want to rotate around and just be close enough that we get something. And what we're going to do, we already talked about this, so you're going to do an open string, and then any closed note, and then any closed note with vibrato. All right? So I'll hit record, and I'll be quiet, and you can do that. Ready? Okay, any other note? Vibrato? Very good. All right, so let's grab that first one here. See if that's what we have. Oh, that's not the first one. How do I get back to where you were?
The scroll bar at the bottom.
Right there it is, the slider at the bottom. It's good to have help. Okay, let's try that part. That was the open string, right? All right, so let's have a closer look at that. That's the one I want. And let's blow it up a bit. Let's stretch it out a little. Okay, so there's what that note looks like in time. That's the time record of that, and it's in stereo, but it's the same thing going on. Now what I want to do is show you the frequency spectrum of that signal. Okay, so this shows you the amplitude, how strong the signal is, and on this side is the frequency. So frequency is in hertz. 1 time back and forth per second is 1 hertz. So, for example, 300 hertz is 300 times back and forth in 1 second, right? Or 1/300th of a second between times back and forth. What we see is we've got a big peak right here, and that has a frequency of 222 hertz, so that was an A. Is that what that string's supposed to be?
Right.
Oh, good. All right, so that would be our fundamental, that's what your ear was hearing. You were hearing that frequency. But you also see, let's see, that's 222. What's 222 times 2? All right, very good. Okay, let's see what that is. 442. Okay, I might have missed it slightly. Okay, that's double. What's 222 times 3? That would be this one. Okay, 666. Okay, what's the next one? 888. Okay? Well, you're going to do some odd stuff with it, but there it is. And there's that one, right? So basically, each of these peaks, and you can see it's really strong. This is a log scale, it's decibels. So this is like a lot stronger than this stuff in between. This is the one you're hearing, but it also had all those other harmonics in it as well. And that combination of things is what lets your brain say that that sound that you were hearing at this frequency is a cello. The combination of those other harmonics is what makes it sound like a cello. Okay? Let me go off of this for a minute. Oh, close. We'll go grab the other part that you did. Oh, that's easy. Okay, this was a, not the open string, but one where he's holding onto it. Let's see if its spectrum looks similar. Okay, I forget what note that was. Do you remember? There's a D. 293, almost 300. Times 2, almost 600, a little less, 585. Times 3, right? 4, 5, 6. This is a little different because it looks like this is the highest one. Still, that's the pitch that your ear was hearing, and this is what makes it just sound slightly different. If you play an open string on a cello, it's going to sound slightly different than any other note played by holding it down. You could probably play on a different string, have gotten the same note out. I don't know about the A, but you know, doing it, and it would sound slightly differently. Let's try the one under with vibrato. So we did the same note, giving a little shake. What do you think is going to happen? Any ideas? Speculation? Do you have an idea? No. Yeah, Drew.
You're going to see some component way down low.
Maybe filling in down here.
Yeah, dealing with possibly with the frequency of the vibrato. But
Any other ideas?
It may not make it into.
I don't know what the answer is. Any other ideas before we
The
look?
peak should be wider.
The peaks should be wider. Right now we have very sharp, distinct peaks, right? Specific frequencies that happen for that note. And if we shift the frequency, the pitch a little bit, you know, which is what you do when you're playing vibrato, we should maybe broaden out those peaks, right? Because we're not looking at this frequency, we're looking at a range. So again, let's look and find out. I want to grab the beginning of the end, but let's see. Nice vibrato, huh? Okay. Well, I don't know. They're not, I mean, yeah, they're broader, but not grossly so, right? Which means probably that you have a really tight kind of vibrato. It's not some operatic soprano, right? You know, it's okay. But still, here you go. It looks pretty much the same in terms of you're hearing this one. That's the second one. It's a little higher. The third one's still a little higher. And basically this combination of things is the spectrum that describes each other.
Just like Drew said, you have a peak lower down.
Now you have to be a little careful because if we go look at this peak
Yes.
right here, that's 60 hertz.
You would have
That's
to
the
really
electricity in the
whip it.
room.
Ah,
That's the fluorescent lights and the wire.
we didn't see that before?
It might have been there, but it's down smaller. And then guess what? We're going to see 120 also. There we go. Right? We see the harmonics of the electricity in the room. All right, so you know that, and you sort of leave that out. Okay? I think so. We also have a viola and a violin here. They're basically the same principles. You'll see the same kind of thing showing up on here. The shape of the strength of the harmonics will be different, and that's what again tells your ear that it's a viola instead of a cello, for example. Okay. Thanks, Sean.
By the way, that program Audacity is free.
It's
And
free
you can
and
download
it's
it
great.
for the Mac, the PC, or in this case, Linux.
Yeah. And there's a lot you can do besides what we're doing here. And I actually haven't gotten anywhere near figuring out all that you can do with it. Okay, so basically we just covered all string instruments. Piano, same thing, right? A piano has a string of a particular length. It's hit somewhere near the end. Oh, I forgot to do that. Oh, Sean, come back. We forgot about harmonics.
Encore.
Encore, yeah. And he's good at this, so that's why he's coming back. While you're doing that, if we had a guitar out here, I would be holding this guitar and telling you the classical guitar players and people who play well, like Drew.
I actually have it if you want.
Yeah, that's okay. But I mean,
Okay.
just from the time. If you pluck the string in the middle, you get a nice pure sound because you're exciting that fundamental mode really well. If you pluck the guitar string way down near its end, you get a much twangier sound, much more country and western sound, because you're exciting more of the higher harmonics. Let's go back to, oh, maybe that's, oh, okay, we can get back here. Remember how funny our time shape looked? And that's because we had different harmonics added up. So here's a case where we just have different sine waves with different strengths. You can see the spectrum of them over there added together and gave us something like this. All right. So basically, again, guitar players doing country and western twang the string way down here, and you're going to tend to excite these guys more. Whereas if you strike it or strum it in the middle, you're going to likely get more of this and less of those. Now what we want to look at is something called harmonics, used in the sense of how you play the instrument. Pick a string. You should play an open string. Okay, so keep that pitch in your ear. What you're hearing is this one. And now what he's going to do is just touch the string in the middle of it and hear what happens. All right? Same string, not pushing down on it, just barely touching. So what happens is he's putting a node right there by touching the string in the middle. He forces this to be 0. And when he does that, this is no longer here. That one's no longer here, that one's no longer here, that one's no longer here, right? So you get every other harmonic. The character changes. It sounds a little more pure, actually. You play the open string and then that harmonic again. Can you hear the difference in the character of that sound? Besides the fact that it went up an octave. It went up an octave because what your ear is now hearing is this one. All right, how about the next harmonic is if he touches the string a third of the way up, it's going to give us this one. It's hard to find. Ooh, I think we even went, let's see, we went, we're like up here somewhere.
Well, there's a harmonic,
Yeah,
there's a
or
harmonic
just-
here, but it's not,
Yes. Depending on where he's touching the string, he's going to damp out all the ones below it and keep only, let's say, that one and its multiples. So that one times 2 times 3 times 4 times 5, right? So it could be jumping up octaves, right, just by touching the string in different places. You want to actually try to slide your finger around? As slowly as so we can see where the harmonics are happening. There's one. There's one. There's one. Yeah? Yeah. Okay, there's our, that's certainly more than my skill ability with this thing, right? Okay, so you got that idea of how you actually make use of this physics in order to do things with the string instrument that's beyond just simply playing the string as it is. And you actually make use of these things. Listen to really good guitar players sometimes. You'll hear them pop these really almost bell tone kind of sounds out. They're hitting a harmonic. They're just barely touching the string and off comes this sound. Okay, I think that's, once again. All right, wind instruments. And again, I'm reminded of something I didn't tell you about. The string instrument is a longitudinal, or sorry, it's a transverse wave, right? The string was vibrating perpendicular to the direction of the string. That doesn't make any sound, right? A transverse wave does not sound. So that vibration had to be picked up by the bridge of this cello, and the body of the cello holds air in it, and it's being oscillated by the bridge, and it's that oscillating air that causes the sound that you hear. So all string instruments have to have something like that. In a piano, it'll be the sounding board. In an electric guitar, it's going to be an amplifier that's to pickups, electrical pickups that are picking up the vibration of the string. And then a speaker in the amplifier will give you the sound. But the string itself isn't making any sound. Okay? It's making the oscillation that gives you the sound. Wind instruments, on the other hand, are going to give you a pressure wave, a longitudinal wave, because what happens is we're going to blow into the end of this thing, and we're going to cause a pressure wave to go down this thing. This is my version of a flute. I'm a French horn player. This is a flute. Okay, so basically, a flute is just a tube. It's got air inside. It's got some holes in it, and if I cover up the holes, basically it's got an open end here because there's a hole on the end. A real flute has a hole where you blow into it. Okay, so it's open to air pressure on that end. It's open to air pressure on that end. What we're going to do is send a wave down the thing. It's going to bounce back and forth, set up a pressure wave, standing wave inside there, right? And that's what is going to be the sound that you hear. So, okay. Recorder, the same thing. The physics of this thing is that we have, now it's a pressure wave. So at one end, the open end, it has air pressure, regular room pressure. At the other end, open end, regular room pressure. Call it 0 if you like, it's really 1 atmosphere pressure. In between, it's going to be either high or low pressure, depending on whether this is a high part of the wave or a low part of the standing wave. So it could be high or it could be low. And there could be nodes in between where there are 0 or, let's say, room pressure in between. So what we have is now a wave set up, a standing wave set up, which the wavelength of the wave is twice the length of the instrument, twice the length of the flute. So for this thing, the fundamental wavelength is that long. Okay? And then what you get is standing waves or modes or harmonics that are 1, 2, 3, 4, 5 times the frequency of this fundamental. Or if you like, the wavelength is half, a third, a quarter, a fifth, a sixth. Okay? Something like that. Okay. And so you get a fundamental, a first mode that's an octave higher, a second one that's a fifth higher than that. There's another octave above that, so 2 octaves above that, a third, another fifth. There's that funky one that doesn't quite work. Another octave, another, well, I don't remember now if it's a third or something above that. Okay? So you get the same kind of idea. You get the same kind of harmonics with a flute that you get from the guitar. If you open up the holes on the flute, what you're doing is you're basically shortening the flute. By opening it up, instead of having a length like that, it now has a length of wherever the holes are open. And so as I shorten the length of the flute from to something shorter, oops, sorry, there it is, pitch goes up. What I just demonstrated to you accidentally is that the way you get an octave higher on the flute is you overblow it, right? So, but now I'm going to hurt your ears. Oh, right. Okay. So what I did was, if this was the fundamental, by blowing harder, I was giving you this one, and by blowing harder still, I was giving you that one. Okay, primarily what you hear. All right. Should we do this? All right, we'll use this one. Tell you what, since I'm not very good at it, I'm going to just not cover the holes. It's going to be a flute that's that length. All right, whatever the highest note is here. Back to Audacity. Yeah. There we go. Well, that looks kind of complicated. All right, spectrum. All right, let's see. I guess I was probably playing this note. I really don't know. So that's kind of a high, oh gosh, C sharp. That's bad. But anyway, 1100 hertz. What's times 2? 2266. All right, that's this guy. All right, 2270. What was it, 11 something? So times 3, probably there. Times 4 is going to be one of these guys. Times 5, times 6, times 7, times 8, times 9, times 10, times 11, times 12, times 6. They're all in there, right? You're hearing this one, but they're all in there, and they look different than the cello. Thank goodness this thing sounds different than a cello. It sounds different because of the, well, probably, I kind of do it in a harsh way, right? So that's probably why we have so much going on over here. We have a lot of harmonic overtones going on, and it didn't sound like a nice, beautiful, I probably should have done this one, right? Probably would have sounded better. I'm not very good at that one either. Okay, so there's a flute. Nah, we did that. Oh, I'm not, oh, I see. Go back to the show is what I'm going to do. Okay, there we go. That's a real flute. That's better than what I just did. Okay? All right. Clarinet. My lovely wife here is a clarinet player. Let's just hold it up here. This is Carol. So, Encore. So the clarinet has a reed on one end, and you're going to blow on the reed, and it's going to cause an oscillation. It's a really high pressure oscillation. Okay, so you're blowing on this thing, and it's bouncing back and forth. The other end is open to the air. So what we have is a cylindrical tube. Hold it up so we can see that it's basically a straight line. Okay, so a cylindrical tube like this that's closed on one end and open on the other, so that the reed end is a high pressure part and the open end is a low pressure part. Or if you like, the amount that the air is moving, it doesn't have to move very far near the reed, and it's able to move a lot at the other end. Okay, so what that means, oh yeah, I forgot I had this thing. Let's go here. There. Nice little animation. Of, again, a closed tube and an open end, closed end and an open end. It's not showing you the standing wave, it's showing you a traveling wave going up and down there. But what you can see is that when it gets to the end of the tube, okay, now when it's dark, that's a high pressure wave. So you see the high pressure wave come out here, but it actually reflects back as well. So in other words, this part of the air right here gets pushed by that wave and actually pushes right back up the tube. So we do get that standing wave, the thing we were doing with the slinky, even though the end of the tube is open and one end's closed. One of the things you can see here is that it takes 4 times back and forth for this wave to return to its original. So for example, when this heavy one comes out right there, that's 1, 2, 3, before I get the heavy one again, 4, and then it returns back over again. Okay? So the cycle of doing the same thing, in other words, the high pressure wave coming out of the end, takes 4 times back and forth in this clarinet before you before it repeats its cycle. Okay, so the physics is high pressure end, low pressure end. So the wavelength of the fundamental mode of a clarinet isn't twice the length of the instrument like it was with this. It's 4 times the length of the instrument for a clarinet. Right? Not only that, but the next higher mode, the one that has a node in the middle, can't really happen because it has low pressure at this end and low pressure at this end, right? It needs to be high pressure at this end. So this one isn't going to happen, at least not well. The next one that's going to happen is this one, the next mode, the one that has 2 nodes in between, or I guess it's 2 nodes there, right? So that one will work, high pressure here, low pressure there. This one doesn't work, and that one does. So for a clarinet, the wavelengths are 4 times the length of the clarinet, and in principle, you get every other harmonic. You get the 1st, the 3rd, the 5th, the 7th, the 9th, stuff like that. Okay? Just like the flute, just like the guitar, if you put your fingers down, what you're doing is you're shortening the length of the tube by opening holes. So now instead of the low pressure end being here, it's wherever the hole has been opened. It's a little more complicated than that for a clarinet because modern clarinets have lots of extra keys and holes to help the intonation of them. It's not this anymore, right? And this didn't sound very good anyway. Okay. There is, okay, remember when I did this? Okay, low note, overblow, octave higher, right? In principle, you could, I suppose, do that for a clarinet. What it does instead is it has a register key, a key that you open up that opens puts a note in the middle, kind of like playing that first harmonic, putting down the finger on the string in the middle of it. except instead of giving you the second harmonic, it gives you now the third, because we only have the first, third, the fifth, the seventh, right? So if we open the register key, what happens is you damp out the fundamental, and you're left with the next one, which is an octave and a fifth higher. And so what that means on a clarinet, when you go, you call it over the break, right? Below the break without the register key, and then above is with the register key, not just an octave. Okay. You're on, right? We want to record the clarinet now. All right. Okay, come over by the, any note, something low, I think, okay? Ready, go. Lovely. Yep, that's it. It's not a simple sinusoid. Let's look at its spectrum. Do you know what concert pitch? You know what that was? A? Okay. So here's what you were hearing. It's an F. It's all right. It's all right. So an F, 173 hertz. What's 2 times that? 2 times 173. 3 what?
46.
346. Let's go see what the next one is. 346. What's this over here? Nope. 518. Hi, why? Well, here's 346 right there. It's that little thing in between, right? Because this is the first mode, the fundamental. This is the first that doesn't really work in a clarinet. There's the second. There's the third. Look, it's down low. Or sorry, wait. First, second's dead, third, fourth, fifth. So every other one is high, and the ones in between are low, and this one in particular is really low. Okay? So that's the way a clarinet works. You only get every other mode. There's a little bit of the other ones in there, and it probably has something to do with the design of the instrument, the way the mouthpiece is shaped and things like that, to try and give you something of that. But that, again, is what makes the clarinet sound like a clarinet. Every other harmonic. And if you notice, she can play really low on this thing. For the length of that instrument, it's about the same length as a flute, maybe a little longer than a flute. But she's playing an octave lower because the fundamental wavelength is 4 times the length of the tube, not 2 times the length of the tube. So it's a double, or a halving, right? Okay. That's good. Thank you. Okay, and that was her another time, so we don't need that. All right. That was a cylindrical tube. Okay. A conical tube. So saxophone. We have a saxophone player somewhere, right? Where's the saxophone? There you go. Okay. Saxophone, oboe, bassoon. Carol has her alto sax, so bring your sax over so we can prove again that it is a conical tube. In other words, it's got a reed on one end, so a high pressure source, same as before. It's open at the other end, but it gets progressively wider as it goes along. Okay? So the standing waves inside a conical tube are going to be different than the standing waves inside a cylindrical tube, and they look like this. So here's the fundamental. The red one is the pressure wave. I'll use this. The red one is the pressure. So high pressure at the mouthpiece, low room pressure at the outside. The next higher mode is here, and you can tell because it has a node in the middle. And here's the next one, it's got 2 nodes, and here's the next one, it's got 3 nodes. The shapes of these are actually Bessel functions. They used to be sine waves, now they're Bessel functions. And it works out, so now the fundamental has a wavelength of 4 times, if that's the length of the instrument, the wavelength is 4 times that, because we're going to go from a high down to here and back up to a high in 4 times that length. So 4 times the length, and we get every harmonic in between. Again, you raise the pitch by shortening the tube by opening holes, okay? In this case, the register key is called an octave key because we have every harmonic. So as soon as you open a hole that's somewhere around here, you're going to kill that one and be left with this one and this one. So the pitch is going to be an octave higher, and it's going to sound every other one. Try it. Don't believe it till you see it, right? What's that? That. Any note you like. And actually, she played that without vibrato. It's hard to do. All right. Oh, it's a little bit more regular than the other one. Okay, we almost don't need to count them, do we? There's the one you're hearing, 233 hertz times 2, 467, 466, okay, times 3, times 4, times 5, times 6, times 7, times 8, times 8. Okay, I mean, all of those are in there, that one note. So your ear was hearing this, but the character of that sound, what makes it an alto sax, is all of this. Soprano sax will have a slightly different set of those. A tenor sax, slightly different. Okay? Questions so far?
Well,
I just noticed I haven't
one
been...
observation that
Yeah.
the other ones, they don't seem to be much weaker. They're almost as strong, right?
You mean the relative strength of these? Yeah, well, some of that has to do with what we call the brightness or the darkness of the sound. Now, when we get to my French horn, you're going to find it really drops off because it's a fairly dark sounding instrument. Carol happens to play sax in a very smooth, dark way. If you played it really hunky, what it would do is raise these up. So you hear more of the higher harmonics. Maybe your baritone sax would do that too. Okay. Okay, summary of woodwind instruments. So we had flute, which is open on both ends, and so its harmonics are very much like a guitar string, except it was fixed on both ends, so we have a pressure wave that's going either high or low in between. So we get harmonics that are related to twice the length of the tube, and we get the first, second, third, fourth harmonic in this case. Clarinet, closed on one end and open on the other. The length, the fundamental, is 4 times the length of the tube, and we only get the odd harmonics. Conical instruments like saxophone or oboe or bassoon, again, 4 times the length of the tube, and you get every harmonic. So in a sense, this is kind of like the flute, but twice as long or twice as low frequency, or therefore an octave lower frequency. All right, brass. Instead of a reed, we have a mouthpiece, right? So the mouthpiece is just an oscillator, so I'm going to blow in it and just, wiggle my lips. Or I could get anything you like. And then I have this tube, and the tube doesn't have any holes in it, and it's got a certain length to it, right? So it's this tube that is going to be the resonator that's going to determine which frequencies will have standing waves in them. So instead of everything, I only get specific ones. Let's see if I can do that better. Let's go over here. All right. Got a few points, which I know it's. Okay, without touching any of the valves. So basically, that's what's called a natural horn. So that's this thing without the valves. And so, let's see. I don't know that I can play the bottom one. I'll try, but I don't think so. I think the first one I'm going to be able to get without. Let's see. Nope. Let's go to the next one. Now. Okay. I'm just going to try and slide up and see what happens. Ran out of steam. has to do with, it's a conical instrument. It has those same kind of bezel functions. Oh, yes, that's what I'm looking for. We don't want to do that. Yeah, maybe we do want to do that. Yeah, no, I'll tell you what. I'm running low on time, so rather than do that, what I'm going to do is show you, I already did this. This is me, okay? So I played A note, and what we got was, this, 2, 3, 4, 5, 6, 7. Notice how they fall off? Maybe a little steeper than the alto sax, right? Not sure, maybe not a lot. And then this is an octave higher. So what happens is there are only certain pitches that you can play on here, right? You can only hear those particular ones. This was one of them. And then this is the one an octave higher. So let's see, what was that? That was E. That's the top picture. Right? No change, no length of the tube, no nothing. All I'm doing is exciting it with a frequency that corresponds to either this frequency or that frequency, because those are the ones that are available for this kind of instrument. So, maybe you've wondered, why do French horn players use the valves with their left hand? Anybody know why you play the valves with your left hand and the right hand is in the bell? No
Always
volunteers?
wondered that.
Always wondered? Okay, because if you remember that earlier picture, it didn't have valves before, right? All it was a coil of tube, and you could only play those certain notes, right? And there's not a whole lot you could do with that, although I must say Beethoven did a great deal with just those notes, right? But to do otherwise, what you can do is move your hand around inside the bell. And if you close it and open it, you can get other ones. Right? No valves at all. So that's why the hand is in the bell. You can get all the notes that were in between those other ones that weren't possible before. In addition, as you get really high, those really high ones, they're not really well in tune. So by having the hand in here, even with the valves, it plays better in tune. What else have I got in there?
So when
what's
you're
that?
reading the sheet music, you know where to put your hand.
No, the hand just sits there. Well, okay. In the olden days, all right, in Beethoven's day, in fact, in Beethoven's day, they used to have two sort of sets of horn players. Ones who were really accurate in those really high harmonics, those up here, right, where you don't have to do anything, they're just so close together. And then the ones who played low, who had to do, right, it was all right hand technique. So those guys had to be really good at this. The others had to be really accurate with, where they're going to hit. Now we have valves, right? So we don't have to be accurate with the right hand. You don't actually have to move it around. I think that's the next picture. Right? Valves. Originally, the valves were intended to swap out this thing right here, which is called a crook. So you had a length of tube, and it would have a certain length of a slide on there, like this guy, and you would just simply swap this one out and put it a different length, and it would make the tube longer. So guitar, string instruments, all the woodwind instruments, you change the pitch by making the tube shorter. Brass instruments, you change it by making them longer. So we had different kinds of crooks that you would put in to change the key. And in those olden days when they were doing things like in Beethoven, you're reading the music along and it says all of a sudden, switch to the key of D. So you take this thing out, you hang it somewhere, you grab another one, you put it in, and then you carry on, right? And that was kind of hard. But now we have valves. The original idea of valves was to simply replace the crooks. So by pressing down a valve, in this case, if I press the first valve, it adds this length of tube. And if I press the second valve, it adds this length of tube. And I press the third, it adds that length of tube. And then you can put different combinations together. Originally, it was just changing the key. So, and then, right? Just different lengths of tube, same kind of harmonics that you had to work with. But then when you put them all together, right, you can get everything else. So that's how we do it now. And yes, you still move your hand around a little bit just to check the intonation of it. flute player's out of key, so you sort of change it.